Welcome to Learn Algorithm Design and Analysis course. In this session, we focus on fundamentals in string matching. The objectives of this session are: we need to learn what is string matching and what are the notations that are required to implement string matching, basic string matching algorithms, naive string matching, finite automaton with string matching, KMP flowchart, KMP scan algorithms. These are some of the string matching algorithms that we are going to discuss. First, let's going to see what is a string matching. Given a pattern P and a text T, pattern is P. Given a pattern P and the text is T, what we have to do, we need to check if the pattern P is completely available in the text T. That means we need to check if P is a subset of T. If P is completely available in the text, then we can say that results in a successful search. If the pattern P is not completely available in the text T, that results in unsuccessful search or a mismatch between the pattern P and text T. So basically, pattern matching or string matching, this is the problem of checking if the pattern P is completely available in the text T. For that, we are going to use some notations. Conveniently, P represents the pattern characters, T which represents the text characters, M which represents the length of the pattern P, N which represents the length of the text T. I and J are indices to index the pattern character P and text character T. So Pi, which indicates the ith character in the pattern P, Tj, which indicates the jth character in the text T. Other than that, we are going to introduce one function called endText function. Writing a function called endText. This takes the parameters t, j. EndText of t, j. This returns true if j is greater than the index of lost character in the array T. So when j is greater than the index of lost character in the array T, then endText of t, j, a boolean function that returns a value true. Otherwise, it returns a value false. Now let's see how a simple string matching works. Let us have the pattern characters P1, P2, P3, Pk-1, Pk, etc. The last pattern character is Pm. Corresponding to the text array, say this is T1, T2, assuming this is Ti, ti plus 1, etc. This is, for example, a t something j minus 1, etc. Here the character is tn. Assuming that there is a match between p1 and ti, this results in a successful match. If these characters are equal, then we need to find the comparison of p2 and ti plus 1. If p2 and ti plus 1 are equal, we need to increment the indices both in pattern as well as text arrays. In case if there is a mismatch between p2 and ti plus 1, what we have to do? We need to report the pattern is not available starting at this index ith position. So we need to move the pattern one position to the right direction of text array, and from there we need to check if the pattern is completely available in the text or not. For example, consider the pattern ps xx yz ts xy xx yx. In this case, first pattern is xx yz, text characters are x y x x y x. We start the comparison from the first character onwards. This is p1 and t1. p1 and t1, there is a match. So next we need to compare. This is index 1, 2, 3, 4. Here also index 1, 2, 3, 4, 5, 6. 1 and 1, there is a match. So increment the indices, right, for both pattern as well as text arrays. p2 and t2, x and y, this results in a mismatch. In this case, the pattern is moved one position right direction to the text array. So writing p like this, xx yz, t is returned x, because starting from the first position in the text array, pattern is not available. Now we are going to check if the pattern is available in the text t starting from the second position. So writing here y, this is y, x, x, y, x. Now this is the region to be compared for the successful match. Second index, this is 1, because at index 1 this results in a mismatch. So 1, 2, 3, 4, 5, 6. Starting from 2, right? So 2 to 5. Y and x, this results in mismatch. So the pattern is not available in the text starting at index 2. Then move the pattern one position right to the text array. So clearly p becomes x, x, y, z, and t becomes x, y, x, x, y, x. Now let's check the comparison. First two characters, this should not be checked. Starting from index 3, 3, 4, 5, 6. We need to completely check if the pattern characters are available. T3, P1, X and X, yes. results in equal, right? Match, success. Then P2 increment its next index in T, T4, X and X characters are equal. Then P3, T5, Y and Y characters are equal. Then P4, T6, Z and X, the characters are not equal, so this results in a mismatch. Then we cannot increment, right, or shift, we cannot shift the we cannot shift, right, the pattern one position right direction in the text array, because here the pattern length is 4 here, text right xx yx. If you increment, right, or if you perform the shift, you can't check from starting from the 4th position in the text, because 4th position x, 5th position y, 6th position x. Only we have 3 characters in the text array. These 3 characters in the text array cannot be compared with the 4 characters in the pattern array. So we need to carefully compare, or we need to minimize, right? We need to find exactly the total number of shifts to be performed. Since here the length of text is 1, 2, 3, 4, 5, 6. Length of text n is 6 and length of pattern m is equal to here 4. We need to find, right, how many number of shifts to be performed. So we need to logically find the number of shifts to be performed as shift is equal to 0 to shift is equal to n minus m. Initial right, this is shift s is equal to 0. Then this is shift s is equal to 1. This is shift s is equal to 2. That is n minus m. 6 minus 4. This is equal to 2. So the last value of shift is n minus m and the first value of shift is 0. So keeping this, we can design the naive string matcher algorithm, which performs a shifting operation and a comparison operation with the pattern and text characters. In case the pattern is completely available in the text starting from some position, then we can report that results in a successful search. There may be more than one successful positions where the pattern is completely available in the text. In some cases, right, the pattern is not available in the text, then you need to report, right, the mismatch occurs. The pattern is not completely available in the text. For example, here A, B, C, D, this is the pattern. Text is A, B, B, A, B, C, D. In this case, text index 1, 2, 3, 4, 5, 6, 7, 8. The pattern characters A, B, C, D are completely available in the text array T, starting at index 5. So 5, 6, 7, 8. These 4 characters are exactly matched with the 4 characters in the pattern array. This results in a successful match. So you need to return the index, right, 4. Return the index, right, j is equal to 4, which indicates that return the index, sorry, j is equal to 5. Returning the index j is equal to 5, which indicates that the pattern characters are completely available in the text array starting at index 5. This results in successful search. Successful search. Suppose if the pattern is x, y, z, if the text is XX, XY, A, clearly the pattern is not available. Pattern is not completely available in the text array. So this results in a mismatch, that is an unsuccessful search. Unsuccessful search. So how long we are going to perform the shifting operation? As we discussed, shift starts at 0 and it reaches the maximum of n minus m. If the pattern is completely equal to the text characters starting from 1 to m in the pattern, that is equal to s plus 1 to s plus m in the text array, then we can say that the pattern P occurs in the text T with the shift S. Otherwise, we need to tell the pattern is not available in the text array. This is the logic of naive string matching algorithm. Now let us devise the naive string matching algorithm. Naive string matcher algorithm. Naive string matcher. Parameters are T and P. What is T? T is the text array. P is the pattern array. Assuming m is equal to length of pattern P and n is equal to length of text T, we are going to perform the shifting operation. For shift is equal to 0 to n minus m, do shift right starts at 0 and reaches the maximum value of n minus m. For shift s is equal to 0 to n minus m, do we are checking if the pattern characters are completely available. Pattern characters from first index to mth index is equal to, in the text array T, shift s plus 1 to s plus m, they are completely equal, then we can print the pattern P occurs in the text T with shift S. Else right, that is a mismatch. Far right closes here, right? Opening and closing curly brace or closing curly brace not necessary, because we have only one if statement under this far. This is the end of the algorithm. So minimum right, maximum value of S right is n minus m. S right starts at 0. We are completely checking if the pattern characters are available in the text array. So here P from 1 to m, this is generally returned because pattern length is m. Characters are assumed P1, P2, P3, etc. Pm. Text characters are assumed T1, T2, T3, etc. Tn. Since shift right starts at 0, 0 to n minus m, we are writing here T of s plus 1 to s plus m. If the text characters starting from s plus 1 to s plus m such that the length is s plus m minus s plus 1 plus 1, that is s plus m minus s minus 1 plus 1, 1 minus 1 cancels, minus s cancels. Pattern length is m, 1 to m. That means m minus 1 plus 1 plus 1 minus 1 cancels. Pattern length is m. Text substring right, taken from the text, whose length should also be m. Then we can say that the pattern P occurs in the text T with current shift value as S, right? If not, we can conclude the pattern is not completely available in the text. For example, 1, the pattern is AA, BC, DE, and the text is AA, BC, DE. In this case, we can find the shift operation. So writing the indices in the text array, this is first index, second index, third index, fourth index, fifth index, sixth index, seventh index, and eighth index. Pattern indices are 1, 2, 3, 4, 5, 6. First shift S is equal to 0. When S is equal to 0, comparing T1 and P1, T1, P1 matches A and A. Then T2 and P2, A and A matches. T3 and P3, right? This results in a mismatch. So shift S is equal to 0 fails. Now putting S is equal to 1 here, S is equal to 1 means P1 is compared with T2, P1, T2, right? There is a match, this A and A. Then P2 and T3, A and A matches. P3 and T4, P3 is B, T4 is A. This results in a mismatch. So S is equal to 1 results in a failure search. Taking S is equal to 2, P1 is compared with T3, P1 is compared with T3, P1, T3, A and A, okay. Then P2 should be compared with T4, A. Then P3 should be compared with T5, T3 is B, T5 is B, okay. Then P4 is compared with T6, P4, CC, right, matches. P5 is compared with T7, DD matches. P6 is compared with T8, EE matches. So it seems A, B, C, D, E. A, B, C, D, E. A, B, C, D, E. This is in the pattern array. Text array after 2 shifts. So in the first shift, write S is equal to 0, starting at first position. Shift S is equal to 1, first character is ignored. Shift S is equal to 2, first 2 characters are ignored. So A, this is ignored. Then writing A, B, C, D, E. Now completely the text characters after 2 shift S is equal to 2. That means starting index is, right, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6. So pattern length is 6 minus 1 plus 1, that is 6. Text, right, substring length is 8 minus 3 plus 1, 5 plus 1, 6. So exactly 6 characters are there in the text array. 6 characters are there in the pattern array. All these 6 characters are matched. A and A, B and B, C and C, D and D, E and E. So in this case, we need to conclude pattern P occurs in T with the shift S, right? So what is the current shift? Current shift is S is equal to 2. P is completely available in the text T with shift S is equal to 2. So we can write the index T of S plus 1 to S plus M. Please understand, T of S plus 1 to S plus M. Putting S is equal to 2, 2 plus 1, 3, 3 to 3 plus M. What is M? M is 6. 1, 2, 3, 4, 5, 6, 7, 8. S plus M. S is right 2. 2 plus M is 6. Okay. 2 plus 6, 8. So T from 3 to 8. S is 2, not 3. 2 plus 6, right? So T 3 to 8. Starting from index 3, right? Up to right index 8. Totally 8 minus 3 plus 1. That's the length. 5 plus 1. 6 characters are there. So the pattern occurs in the text T with the current shift values are 2, and its range or index is exactly at S plus 1 position. S is 2, 2 plus 1, third position. The last character in the text array to be compared is S plus M. Then only we can have the length S plus M, right, as we obtained here. S plus M minus last index minus first index plus 1. This is L minus last minus first plus 1. S plus M minus S plus 1 plus 1. So that we have exactly M characters are there to be checked in the text array T, corresponding to the same M characters in the pattern array. This is one example, right, where we have a successful match. Suppose consider this example. Consider this example. Second one. Pattern is ABCD. Text is XYZX. Having here the length n is equal to 4. Here also the length m is equal to 4. How many times we need to check, right? That's a question. First we need to check A and X. This results in a mismatch. So shift is equal to 0. A is not equal to X. Condition fails. Then shift is equal to 1. A and Y not equal. Condition fails. Shift is equal to 2. A and Z. Condition fails. Shift is equal to 3. A and X. Condition fails. Problem is, do we need to perform these shifts, right? That is the question. Are these shifts necessary, right? That is the question. Since 4 characters are there in the text array and 4 characters are there in the pattern array, right? Now shift S is equal to 0. This is valid because the algorithm starts with shift S is equal to 0. The maximum value of shift is n minus m. Shift S is equal to 0 to n minus m. N is 4. 4 minus 4, 0. So 0 to 0. Only this 0th shift is valid. These remaining shifts are invalid. They should not be performed because we should not have enough number of characters in the text array for the comparison. So terminate the process when shift reaches a value n minus m. Then consider this example, third one. Pattern is AB, AB. Text is AB, AB, AX. So finding the shift value S is equal to 0, ABA, AB, 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 right? So it seems in the first shift itself, the pattern characters are completely matched with the text characters AA, BB, AA, BB. So shift is equal to 0, right? This results in a successful match where the text characters are T, S plus 1 to S plus M. T, S plus 1 to S plus M. Since S is equal to 0, putting here, we can get T from 1 to M. So the first M characters in the text array, since here M is 4 and N is 6. First 4 characters in the text array are completely equal to the pattern characters. In this case, the pattern P is completely available in the text T with the shift S is equal to 0. So this results in a successful search or successful match. This is the naive string matching algorithm. So the purpose of naive string matching algorithm is to check if the given pattern is completely available in the text T. If it's so, it finds the location. In case the pattern is not completely available in the text T, this results in a mismatch or unsuccessful search.